Okay, so I hope all of you can hear me. This is always the first statement one makes, and by now you would be all familiar with the statement of the speaker asking whether one can be heard and one can be seen. But let's assume that all those things are happening. And I also realize that this is the last week of your summer school and refresher program. So you have gone through a lot of things, and I think it's time before I start giving you this talk to think a little bit back on what we're doing. And given that there are still a significant number of participants attending this, let us try to figure out what is the summer school about. Why are you attending this talk? And what is the reason for logging in and zooming in and using your bandwidth for hearing my talk instead of much more productive things which you could be doing otherwise? First of all, let me re-emphasize to you again that any summer school or refresher course is not meant to teach you astronomy. Let me repeat that. Any such course, refresher course or summer course is not meant to teach any of you astronomy. And the reason I'm saying that is that I've been learning astronomy for last 25 years and I still don't understand the subject and I'm still learning. And if any of you can understand or learn astronomy in 2 months, that would imply that I am very dumb, and I don't like to be called dumb. So, what I would suggest, so hence I would say that that cannot be the motivation for having a summer school or refresher course. The motivation is probably something different. Is that whether you really want to spend the next 25 years of your life learning this subject? And since it's a very difficult question to answer, and you should really think about it very carefully, a summer school or is a kind of a thing to tell you whether you should be doing that. And for those people in refresher courses and who are already advanced in teaching, that is also uh, a summer school or refresher course is to teach you that whether you think that this is a field which would be interesting enough for you to inculcate in your curriculum, or if it is a field much more interesting where you would like to do some work on it as well. So that's the basic motivation. The motivation is that at the end of it, you should be able to answer the question that whether you are interested in astronomy or not. And hence, what we'll try to show here is what are the things which really motivates us to spend so many years of our life working on these kind of subjects. And by that, you could probably decide that, oh, of course, there are many people who would want to spend so much time doing astronomy, but I'm not one of them, which is a perfectly valid and good decision to take. Or you may say, no, this is something which I want to consider seriously. So if the summer school has helped you decide on these two things, it will be a very good. So I will, although you have heard so many talks and lectures already in the, well, I was thinking I'll talk to you about something which of course you already would have heard about. Several things may be repetitions, but anyway, it's my perspective on certain aspects. And I know that one of the big motivation things in for young people is that there's a dream that some days, if you work on the subject, you will get a Nobel Prize in physics. And the Nobel Prize is the ultimate prize, and you will. That is an ultimate dream to have. Of course, even deep inside you realize that that is highly unlikely to happen because it's given to very few people. But also, there's a kind of a mistake in that dream, in that the Nobel Prize is not given to a person. I mean, it looks like it's given to a person, but a Nobel Prize actually is given to an idea or a concept. And I want to emphasize that it is the idea and concept which is more important than the particular person who has been getting it. So that is one of my. So I'm going to mingle two things, and I'm going to talk about this topic about what I would say, which I call the noble road to observing black hole systems. So I'm going to talk about black holes, and I will start with, although you may have heard about it already, let's talk about what are black holes. Now, to understand that, you have to do a thought experiment, and you have to actually fantasize. You have to have a good fancy on these things. As you imagine that you take the sun, which is a very big object in the sky, huge big thing, which we see every day, and that object, sun, you squeeze it. The sun is a very big thing, but you squeeze it so that it becomes only 1.5 kilometer in size. Now, if you squeeze that sun to that size, that object which will become is by definition a black hole. So let's make it. You take the sun, you squeeze it to 1.5 kilometer size, it will become a black hole. So the first thing we note is that black holes are small and they're very dense because all the matter is put in a very small region. And since we know even Newtonian gravity, or even by Newtonian gravity, that the gravitational force is gmm by r square, and what we are doing here is we're keeping the mass of the sun the same, but we are reducing r to a very small amount. The gravitational force on the surface of such an object is very, very high. In fact, the gravity of a black hole can be about 1 followed this many times that of the Earth. It's a very, very high gravity. So black holes are objects which are small, they're dense, and they have powerful gravity. So what is the specialty of that? Is that black holes, because of the even light cannot come out of a black hole. And I'll explain a little bit on what does that mean, that light cannot come out of a black hole. But if light cannot come out of a black hole, then no information can come out of a black hole. You cannot get anything coming out of the black hole at all. There's no information coming out. If no information comes out, you cannot. That is why the surface of the black hole is called an event horizon. And event is the universe is made of events. Like I'm giving a talk, this is an event, and this event that you're hearing my talk, you can go out and tell people that you heard my talk. But whatever happens, whatever things happen inside a black hole cannot be known to an outside observer or to us who are outside a black hole. So hence, all events which occur happen for us outside the black hole. Therefore, it is an event horizon. Horizon means something beyond which you cannot see, and event horizon means that all events beyond that you can't see. So that's why it's called an event horizon and not a black hole. And so the surface of black hole is called a event horizon. Now, an important aspect of a black hole is that it has something called gravitational redshift. Let me explain that. And the way to explain this is that suppose, let's do another thought experiment and say that suppose I am standing close to a black hole. Mind you, I am not inside a black hole, I am standing close to a black hole, and I shine a torch away from the black hole towards some other distant observer. Now, the light can of course go out because I am outside a black hole, and since I'm outside a black hole, I can send light to the distant observer. But as the light travels, it will face the gravity of the black hole, and the light will lose energy. And when light loses energy, what we understand in physics, it means that its wavelength will become longer, frequency will decrease, or in other words, it will become redder in color. So if I shone a blue light close to a black hole, by the time it reaches a distant observer, it will be reddish in color. The key thing is, if I move slightly closer to the black hole, but still outside the black hole, the amount of redshift or reddening will increase because now the light has to work more against the gravity of the black hole. And as I go closer and closer and closer to the black hole, eventually, as I'm getting very close to the event horizon, the amount of reddening which happens is infinite. So that means that no matter what kind of a frequency of light I send from very close to the event horizon, by the time it reaches someone far away, the light would have become completely at a very large wavelength or infinite wavelength, which means that the light would not be there at all. It is in this sense, and only in this sense, that we mean that light cannot come out of a black hole. Anything. So it's a limiting case on that aspect. It's not that light goes out and then falls back in or something like that. It's just that the amount of energy required for light, for an observer outside, to see it coming, it becomes red. I mean, it becomes so red, that is, the wavelength increases so much that we cannot see it anymore. So, to summarize, just three aspects of a black hole I want to talk about. Black holes are small, dense, they have very strong gravity, and they have a concept called gravitational redshift, so that light coming from close to a black hole loses energy as it goes to infinity. Right? For this talk, that is all that I'm going to talk about black holes right now. I'm going to talk only this much about black holes because I'm going to ask two important questions. The first important question is, can black holes exist? The first thing is that when Einstein gave his general relativity in 1918, a few years later, then after that, there's a German soldier called Karl Schwarzschild who said that if Einstein was, and soldier means he was actually in the war, in First World War fighting, but in those days they could sit in the trench and keep waiting for the enemy to attack. So during the time when he was waiting for the enemies to attack, he did some calculations and derivations and found that there is, if Einstein's equations are correct, then you could have a mathematical formulation of something called a black hole. I'm not sure whether at that time when he came out, even Einstein was knew about this result, but not many people cared about it. No, it was not considered important at all. Now, why was it not considered important? It was not considered important because of the very first question, very first statement I made when I started this talk, when I said that you imagine the sun and you squeeze it to 1.5 kilometers. Now, the sun cannot be squeezed to 1.5 kilometers. It's impossible. So, black holes, so these are impossible things, and hence nobody is bothered about them. You see, physics is a study of real objects in physical systems. We can always fantasize things about what can happen, but in fact, a lot of the study about the theory, the equations of black holes were part of mathematics. They were never considered seriously as being part of physics in general. All this changed dramatically when a young man from India, he took a ship from Chennai, or at that time Madras, to England, and when he was going there in the ship, he made some calculations and he found that in a particular situation, a star, when it loses all of its energy, will collapse, and when it collapses, it can form a black hole. He didn't say black hole will collapse completely, and then the possibility of a black hole will be there. This was dramatic, and for this, S. Chandrasekhar got his Nobel Prize in 1983. But mind you, one thing I must point out, that for this statement that can black holes exist, to which he answers yes, he got his Nobel Prize, but that was more than 50 years or something after he had actually first made that statement. But even then, after Chandrasekhar has answered this question, that can black holes exist, there were of course people who didn't believe him, and you may have heard a lot about those arguments between Chandrasekhar and Sir Eddington about whether he's correct or not correct. The majority of the physics people, the bulk philosophy of the people, did not care about this question. There were only few people who were interested in this question actually. Whether black hole, is Chandrasekhar correct or not correct? Why was that? That is because a very important question was not answered, and that is, do black holes exist? You see, there's a distinction that if you have an object which can exist, like Chandrasekhar said, doesn't mean that in nature it will exist. You can always imagine great things. You can always imagine that uh, there is a 200-story building in your hometown, your town, but that is it's just imagination. It can exist. You can make such a building in your place, but it does not is not there, so it's not to be bothered about. The real important question was, do black holes exist? And then nothing happened till 1970s when this question, do black holes exist, was being looked upon more carefully. And from 1970 to maybe around 2000, 2005, for 35 years, people worked on this. And of course, there's no mystery on this. I can tell you that the answer to that question is yes, black holes exist. What I will do now is give you an idea of what happened in those 30, 40 years and even up to now, that how did we know the answer to this question, that do black holes exist? So what I will do is I will, instead of giving you a talk, like a general seminar talk, I will try to take something like a lawyer, and once as a lawyer, I will try to answer, give you evidences that why. Uh, as a lawyer, I'll like to argue that black holes exist, and you will be the judges and the jury, and you will decide whether the evidence which we have got forward is real or not. Okay, so let's start that way. I will take questions in the end because the online things are becoming very complicated. So I will just take questions and answers in the end if you don't mind. Now, just remember your question and answers, and we will talk about it now. So now the court case starts, and I have to give the answer. Now, if you want to ask a question like, can black holes exist? You should go and do some calculations, like Chandrasekhar did. And you need a pencil and paper actually. But if you want to ask a question like, do black holes exist? You cannot sit in your room and do calculations. That's not work. Because you have to look for them. You have to search for them. Physically go and look where they are, how they are, right? Since there are no black holes in the Earth, we have not found, it's unlikely to find any black holes in the Earth. We have to look for black holes in the universe. And so here is very old map, 1970s, of the sky. Now this is the left side, if you can see my mouse, is an image of a sky made in 1970s, 74, 75. And the sky is a dome, just like the Earth is a globe, the sky is a dome, is a sphere. So when you collapse it to a piece of paper, it looks like this kind of a map. So this is the whole sky of the map. But this is not the sky which you would see if you went out to any place and any position. Because this is the kind of sky which you would have seen if your eyes could see X-rays. And even if your eyes could see X-rays, you would not see this image because thankfully the Earth's atmosphere absorbs all these X-ray emissions. And therefore, to observe this kind of the X-rays coming from space, we needed satellites. In fact, that is the reason why my story starts in 1970s, because by then the satellites were in a position of certain that we could now look at the X-ray emission from the skies. Now, the way this map is made is that on this line here, on this what we would have called the equator on Earth, along this line is the Milky Way. The Milky Way, as you may have already known, is our own galaxy, which we live in. It's a collection of stars, and if you look in the sky, it comes as a band across the sky. It's a very beautiful sight. If any of you have not seen the Milky Way, please make it a point to see the Milky Way. It's some wonderful sight to see. But this map is organized such that on this line is the Milky Way, is our own galaxy. So it is turned in an angle such that the Milky Way goes along this line. And as you can see, there are many, many bright sources here which are near our Milky Way, so they belong to our galaxy. They are these point sources. On the right side is a map from 1980s, already 50 years ago, when by then we had known that there were many, many, many more X-ray sources in the universe than in what we had known in the 1970s, but that's a different story. Let us go with these bright sources which we can see out here. These bright sources, some which we see out here, they're often called X-ray binaries. I'll come to a point later why they call X-ray binaries, but let's try to understand what are they actually out. When you look at these objects, the first thing that you notice about these X-ray binaries, which are objects in our own galaxy, just for this image, see, just for the fact that without knowing anything else, just for the fact that we detected X-rays from a Nobel Prize was given, and that too in 2002. Remember, I told you that 1970s was done, and after 32 years, Ricardo Cocconi got a Nobel Prize for pioneering contributions which led to the discovery of cosmic X-ray sources. Okay, let's go to those X-ray binaries, and each of those X-ray binaries has a total amount of energy coming out because they're coming out in X-rays, radiation. This amount of energy coming out is 10,000 times that of the sun. That is, the amount of energy per second being released by any of those single objects is 10,000 times more than the sun's energy, which is amazing. That means there must be a very, very big star or a massive star or a collection of large number of stars to give you such kind of luminosity. However, they are variable. What does variability mean? That they can flicker. The best example of variability is that of a candle which is in a slightly breezy atmosphere. So the candle will flicker. It'll just keep going on and off. Brightness will come down and up. If it is there's slight wind, the candle keeps going. That is called flickering. And many of these objects are flickering in a similar way. Now a candle, when it flickers for about in time scales of a second, which means that half a second, 1 second it is slightly low, then next second it is bright, then 1 second is off, 1 second. So this is the time scale. It flickers in time scales of 1 second. Now if I told you that a sun will disappear in a second, you know that's not possible. A massive objects like the sun cannot disappear instantaneously or very fast. But while a candle can actually be snuffed out or changes luminosity or changes flickering on 1 second. So we got a natural idea that small things can vary in time fast, while big things will take a long time to vary. This concept is put rigidly in physics because we know that the speed of light is a maximum. So the way we put the statement is that if an object is varying on a time scale of time t, then its maximum size should be the distance traveled by light on that time scale. So for a candle, if I say that it's flickering in 1 second, when I say that a candle must be smaller than the distance traveled in light by 1 second, which is 300,000 kilometers. This is not a big statement. A candle is obviously smaller than 300,000 kilometers. 300,000 kilometers and a candle are very, very different things. But this is the absolute limit. No object can move faster than 1 second if it is larger than 300,000 kilometers. However, these objects which are talking about are variable not on seconds but on milliseconds, which means that the size is less than 300 kilometers. So let's take a pause and look at what we're talking about from this evidence. That there are sources in the sky which are 10,000 times brighter than the sun, but yet they are smaller than a single state of India. 10,000 times brighter than the sun, smaller than 300 kilometers. This is an astonishing fact that we have to register, and there is very simple logic about this, that this cannot be violated. Before we start wondering on what this means, Let's go back and look at the sky again, and you'll find that outside our galaxy there are other sources which also are giving out X-ray sources, and these X-ray emission from the other sources are called active galactic nuclei, which you have already heard about, but let me explain again. Active galactic nuclei are the centers of some galaxies. Only a few of our we live in a certain galaxy which is called the Milky Way, and there are millions of other galaxies in the universe. The centers of only few of those galaxies have a bright light coming from them. Those objects centers which have bright light coming from are called active galactic nuclei. So if we look now at those centers which are very bright, the amount of energy coming out of a AGN or activated nuclei is 10 times that of the whole galaxy. Now let me remind you that a typical galaxy like our galaxy has 10 to the power of 11 stars, which is how much? 10,000 million stars? No, 10,000. 10 to the power 11 is 10,000 million stars or 1,000 billion stars. Now, this single source is more than 10 times that of the galaxy. So, it is about 10,000 billion times more brighter than the sun. 10,000 billion with a B times, or 10 trillion times that of the sun. Even though it is so bright, it is variable in seconds. Within minutes it changes. And you know that light takes about 8 minutes to come from the earth to the sun, and from the sun to the earth, 8 minutes. So this object is much smaller than the distance between earth and sun, but yet is brighter than 10 trillion times that of the sun. This is just awe-inspiring, massive numbers. You have to wonder what they could be. So let's start thinking of what they can be possibly be. How can anything produce so much energy? One of the standard ones is nuclear burning, which is nuclear fusion, and this is how hydrogen bombs are made. This is also the way how the sun gives out its energy. That is, hydrogen atoms are fused and they form helium atoms to give out energy. So if you take your textbook physics, and the amount of energy which is released if you fuse two hydrogen atoms together is 6 × 10⁻18 ergs per gram. That's a lot of energy being produced. But by far, this is not the most powerful source of energy in the universe. The most powerful source of energy in the universe is strong gravity. What does that mean? Gravity is a source of energy the same way as we get energy from hydroelectric power. You put things in a potential and you drop them, put water in a potential and drop them, you get energy out. If a meteorite or something strikes Earth, it is not that the meteorite was speed of meteorite or energy of meteorite, but as it falls toward Earth, it gains energies, and that can be destructive towards the Earth. So gravity is one way by which you can convert and produce energy. If you take a piece of matter and throw it, let us say, towards a black hole, by the time it reaches the barrel, its total kinetic energy which it has gained would be about 1/10 of its rest mass, or 20 times higher than this number for nuclear fusion. So strong gravity is the most powerful source of universe. So now this is what I want to show you as evidence that we have objects in the universe which you can see, which are very small. They are about less than 300 kilometers, but 10,000 times brighter than the sun. There are also objects in the sky which are smaller than the Earth-Sun distance, but they're trillion times more luminous than the sun. And on the other side, we have objects called, we are imagining objects called black holes, which are very small, very compact, but have very strong gravity, and hence can be a potential source of energy. So, since these are powerful sources and compact sources, the evidence we have given is that these must be having a black hole in them. So does that mean so in the whole thing? Before we ponder for this question, here's a kind of a picture to guide you what really we think is happening. That right in the center of here, there's a black hole, and for an X-ray binary, let's say then there is a regular star. This is like a sun or some regular star, which is going around this black hole. And this star is so close to a black hole that matter can now be moved from there and falling towards the black hole. But as matter falls into a black hole, it has angular momentum. Remember, the star is going around? Because it has angular momentum, the matter will not fall directly to the black hole but form a ring around it. It will form a ring, and actually in process, this ring will continuously keep going around. In fact, it would have been something like the rings of Saturn. However, this is hot gas, and because it's hot regular gas, the gas has viscosity or friction. And because of viscosity and friction, this gas will spread. And as it spread, it forms something like what is called a disk, which we technically call an accretion disk. And as it falls towards the disk expands and moves towards a black hole, which means that the matter is falling towards a black hole. And because of friction or viscosity, this gas will get hotter and hotter. And by the time it approaches close to a black hole, it becomes so hot that it starts giving out X-rays, and that is the X-rays we are seeing. So this is a beautiful story we have thought about all this. There's only one slight problem with this story. And this one problem is apparent from anybody who has seen this, that this, what I'm showing you right now, is not real. It's a painting. It is a drawing by somebody. It's not a photograph. It is our imagination that we are seeing. We think that something like this happened. And in a court of law, no such things are allowed. You can't make a drawing. You have to show real proofs, real photographs. So from now on, I will only show you, I promise, because you are judges of a court case, that I will no longer show you any images. I will show you real proof. So let's go back and say that finally, of course, we know that there are objects in the sky which are very, very bright but very, very small, and I know something called black holes which are very, very small and have the potential for creating energy. So that proves it right. This kind of evidence in legal terms is called circumstantial evidence. You see, it is not sufficient for you to say that Mr. X could have killed Mr. Y and hence Mr. X is a murderer. This is called circumstantial evidence. Yes, you have proven that he could have killed, Mr. X could have killed Mr. Y, but that doesn't mean that Mr. X is the murderer. Similarly, while you have shown that it is possible that these objects could be black holes, you have not really shown that they are really black holes. So people were still skeptical and wanted more real proof on these things. So how do we get more proof on this? The key thing is some of these black holes don't have matter falling onto them. So they don't have an accretion disk like this. And if they're not, they're black. You don't see them. But however, even if they are black, you can sense, you can feel, you can infer the gravity, strong gravity around them, and hence we can probably argue with that. So let's take a look of this real photograph. This is from Hubble Space Telescope, again very old, 30-40 years old photograph of a galaxy far, far away, where they saw a ring of gas. Now this ring is not the accretion disk. This is a ring like a rings of Saturn. This ring of gas doesn't have too much viscosity because it's far away from the central object. And what they could do is, from each ring, they could measure by Doppler emission that this ring is rotating. And because it's rotating and is stable around something, there must be a strong gravitational force in the center. From this strong gravitational force in the center, they inferred that there must be a strong gravity, which is most probably something like a black hole sitting here. This was one of the Hubble Space Telescope's most amazing science discoveries, but yet a lot of people were not impressed. There are several reasons why they were not impressed. First of all, this is a galaxy far, far away, and you can see there's very fuzzy image. Even though it's HST, you really can't see anything very clearly there, right? You can't visualize it. So maybe it's all imagination of scientists. Maybe it's not really there in the whole thing. So the question being asked was, why can't we see it can we show us some better proof of existence of black hole? And the idea was, why don't we try and look at the black hole in the center of our own galaxy, the Milky Way? There were two problems with that. One is that the universe is a very dirty place. It's actually very dirty. There's a lot of dust around. And what happens in dust is, if you have gone in the evening when there's a lot of dust around, then it blocks the light. And a lot of lights can be blocked. And the center of our own galaxy has a lot of dust in it and gas. So we can't really see through it properly. That is not a major problem. You can use infrared vision infrared light to go and deeper and see what is happening in the center of it. But that was the other problem is that you can't get a very sharp image. The reason why we can't get a very sharp image of the center of a galaxy is because of the concept of stars twinkle. Now, why do stars twinkle? Stars twinkle because as the starlight enters the Earth's atmosphere, it refracts. And as it scatters around, because its wavefront gets scattered, the image in our eye keeps moving. And what we don't see the movement of the actual image in eye, we see a more blurred image. That is why we see a twinkling, which is that image moving around, and there's a kind of a blurred image, and we cannot really see a star very close by, clearly. So the one way to get out of is to go to space, where there is no atmosphere, like the Hubble Space Telescope. But the Hubble Space Telescope is a very small telescope. It's only 2 meters. And that is why it doesn't get good images. And to send big telescopes to space was very expensive. So the one amazing technique they found was something called adaptive optics, which you may have heard about, but let me just quickly explain. What you do is, you send a laser light like this from your Earth towards the atmosphere. The laser light will reflect back. It will tell you what the atmosphere is doing, and based on what the atmosphere is doing, you will take your mirror, which is your telescope mirror here, and slightly deform it. And this deformation is done in nanometers, and this whole thing is done in millisecond timescales. So a laser light goes up, goes back, that whole thing is arranged in a millisecond, and then the whole system is adjusted in a way. By this, you can correct for the atmospheric distortions, so you can stop the twinkling of the stars. You can effectively act as if you are in space by itself. And using this technique, then we could go and look at the center of our Milky Way. And this is what they did in 1992. This is what they saw. The red spot is where the center of our galaxy is. I mean, of course, they didn't see the red spot. It's just there to mark the red spot. What did you see? After using complex adaptive optic technology, which is probably the most sophisticated technology mankind has made. It's just next to the space shuttle and other techniques which have been done. It's a very high technology system, and spent many years. It took 15 years to develop this. And when they saw this, and the most important thing was to see the center of Milky Way, they looked at it, and what they see? Nothing. You see, not exactly nothing. They saw 1, 2, 3, 4, 5 stars. These are 5 stars. These are regular stars. They're garden variety stars. Nothing special about them. The center of a galaxy is a boring place. There's nothing there. But the important thing is, in science, is often you will find something which is boring. There's nothing there. But you have to be persistent. You have to go after it a little bit more. So what people did was, they went again to see it, and again and again and again to the center of the Milky Way to see if something is happening. And they saw this. Mind you, I told you that I will not show you any, it's a very old picture, but I will not show you any fantasy or any pictures of them. These are real images. All that has been done is, right here on the left hand side is the date. On different times of date, they have taken photographs of the center of the gun, and they see this. What do they see? They see that the stars are moving. Mind you, But this itself is not surprising. No matter what you do, stars actually move. They actually move in the sky. What was surprising here was not that the stars are moving, but that they're moving in a particular manner out here. My particular favorite is this one, which was not there. It comes, turns around, and goes back. But one of the most famous of these stars is this star, which is making a beautiful little thing called an ellipse. It's called S2. Now, if you had shown this image to a person about 300 years ago, to a person called Kepler, he would have recognized him because it was Kepler who gave the rules for this thing, saying that planets, when they go around the sun, they go around and in an elliptical manner. Now, there's nothing particular about a planet and the sun. In fact, any object going around the other, they will go around elliptical objects. So hence, this ellipse is being formed because there is some object here which is very, very big and is unseen. At IUCAA, where I'm, we often have programs where there are school students, class 8, 9 students, who come for a week. Come for a week, and they would interact with a scientist and try to get some idea about what science is. Even those class 9, 10 students, 8, class 9, 10 students, if you give them this idea that this is an ellipse which is formed, this is the speed in which it's moving, these are the distances, and the idea was to ask them what is the mass of this object sitting here. And nearly all of them got it correctly, that this is about 2 million times the mass of the sun. So an object sitting here is 2 million times the mass of the sun. And we can't see it. And hence there is now no doubt at all that there's a black hole in the center of the Milky Way. For this, I'll remind you, 1992 we started observations, and for this, in 2020, last year, Renald Genzel and Andre Ghez, they were given the Nobel Prize in Physics for this discovery of the discovery of a supermassive compact object. And all they did was they took photographs again and again and again. Not them, but remember, it took all the adaptive optics, all the technology was put in to get this, and we have got it. But do you remember something interesting? That the Nobel Prize statement said supermassive compact object. It still did not say a black hole. And this was a fair amount of controversy because people think that now let us not be off. What do you mean? I mean, now we know for sure these are black holes. But still, the Nobel Committee was very careful, said supermassive compact object, because that's all you have found. You have found a big, massive object which is compact. You do not know it's a black hole. What about that event horizon thing? What about that one? What about that time and space gets warped as you see in the movies? No such discovery were made. So we call it a supermassive compact object. How would we ever then know that there's a black hole ever in the system? And what would convince a jury like you? Perhaps a photograph, right? So not a painting, but what we need is a photograph. The problem with a photograph is that if I want to take a black holes are, let me just go back here to this painting for a while. Black holes are tiny objects in the sky, right? Now, if you want to take a photograph, you need to have a camera which could detect those, would have a very good resolution. Angular resolution should be very good. What does angular resolution mean? It means simply that, like if you have a good cell phone and although your friend could be very far away and you take a photograph, you can still make out his or her face. That would mean that the angular resolution of your camera is very good. What kind of angular resolution we would require to take a picture of the, let's say, the black hole in the Milky Way center is about 0.1 milliarcsecond. Let me remind you what an arcsecond is. And you have 180 degrees is what you know, is one half circle. You divide each degree by 60, you get an arc minute. you divide each arc minute by 60, you get an arc second. Then you divide that arc second by 1000, you get a milli arc second. Then you divide again by 10, you get 0.1 milli arc second. Right? You need cameras of that kind of a resolution, and even that has now been done. And what we have done now is that there's something called Event Horizon Telescope Collaboration, which has got this beautiful image last year. This is the image of not of the center of our galaxy, but the center of our very nearby galaxy M82. This one, and you can see this black hole here. This is actually the surface of the event horizon and light moving in, and this is a gas going around the black hole. And based on this motion, one can actually say that this black hole is not stationary but is spinning. And we can now figure out that we have taken a photograph of the black hole, and this was done last year. So in another 25-30 years, I'm sure that this image, sorry, excuse me, would get a Nobel Prize for physics. But the idea is, again, it's not a people, it's the concept that we have been able to, as human beings, we have been able to achieve the ultimate thing which nobody could have ever dreamt about 10, 20 years ago, that we have managed to see a photograph of a black hole in the whole thing. And if there was any other proof to be remaining, what we have done is, you must have heard talks today itself about this, that now using gravitational wave detection, we can actually hear, not see, hear two black holes merging. And when the two black holes merge, there is a signal, a very faint gravitational wave signal which is picked up, which has a particular kind of a shape. And mapping that to a real detection we find, we now know that we can now measure many black holes which have started merging. And for this, the Nobel Prize was given in 2017 to these three scientists for detecting black holes. So in the end, this long journey, we have now come over 30-40 years. We have now understood that there are black holes in the sky and everything. So, but however, there are some issues, and I would like to talk a little bit about those issues. Okay. Now, why does this system vary in milliseconds? Why does the matter here move around in millisecond variability? And if they're moving in variability, how does Einstein's general relativity modify that variability? Can we test Einstein's theories of space-time and all those curvatures out there? Can we really figure out, and do we really know why this matter is moving in like this, and what is the structure of the system? We don't. These are the important questions which we don't know about. If that's looked a little strange, you see this thing called, this blue little thing in this painting. This blue little thing in the painting is called a jet. Let me say something about it. See, physics was, when you were in school, physics was a very interesting subject because it is not a definition-based subject. You don't just say, like sometimes boring classes in biology, sometimes we used to say that, or the way it was taught was very poor, that here's a rose, and rose has 4 petals, and that's it. You don't understand. So you say, so what? But what you don't understand is that what I would like to know is that we sometimes have to work like that in physics because of our ignorance. There is this thing, there are these things called jets, and we observe them clearly. We see them. We have been observing them for the last 40 years. What are they made of? We don't know. How are they produced? We have no idea. When are they produced? We don't know. Are they connected to a black hole, or are they connected to the accretion disk? We don't know. What is the energy source? They are very powerful things. Are you telling me that black holes can give out particles and matter? Well, not really, but it seems so, because we are seeing them. But they may not be connected to black hole. They may be connected to the accretion discovered. How far up did it go? Very far. Are they more energetic than the whole systems? Yes, they are very powerful source of energy. But what are they made of? How are they produced? We have no idea. So despite 30, 40 years of work, we have not understood anything much about these things. These are the many unanswered questions in astronomy, which we are trying to do. And many of them can be answered by looking at exotic things like X-rays energies. So at present, we have so many X-ray space observatories up in the thing, named after great people, X.M. Newton, Chandra, and all these things. This image here is of particular interest. This is AstroSAT. This is India's first space observatory for astronomy, and it has got 4 satellites. And one of its primary mission is to check the variability of black hole systems and to understand why the systems are varying. And from that variability, can we understand the nature of gravity and strong gravity in the whole thing. So there are mysteries ahead, and we have to find out. So before I stop, let me ask you. In this talk, I told you about the things we have discovered or what we have found out, but I have not told you how we discovered them and what is the painful process by which we have to go through to discover them and to be science scientists, which I will talk in my next class, which is where we will talk about the methodology of doing all this kind of thing. But right now, I will leave you with this image and will take questions for that if you have any. So I think what I have to do is I have to probably escape from here. Oh, okay. I got. Oh, well, let me see. I'll get back to Zoom. So let me share screen back to just this part. And let me see if there's any question in chat. So there's one question by Arpita Saha. Can James Webb Telescope be able to get a bit proper picture of a black hole? A little bit clearer on further. True, it'll get a little bit much better, but not as good as the one which have already been taken in this image, which I showed you earlier of M82X1. We cannot go better than that because the James Webb Space Telescope is going to go to space. It is a next space station. I mean, space telescope, but it is the size of 6 meters. And right now, the telescope which was used there for was on the ground was a 10-meter class telescopes, and between 10 and 6 meters, the difference is in squared. That is, it is 100 versus 36, so twice much more than just 10 meters, and so it will get a better picture, but probably not beat the adaptive optic based telescope from ground. So Arpita, did I answer your question? I guess so.
Sir, I just make a point. The participant cannot unmute themselves.
I see. Okay. So then you'll have to.
Okay. For this session, let me give the permission to participants to unmute themselves.
Okay.
Yeah. Now the participants can unmute themselves.
Okay. So, but let me take the question from the chat first. Priya is asking, can there be some analogy between atoms and black holes? As the clearest picture of atoms are released recently by which looks quite similar to the black hole image of M81. Actually, they don't. Okay, let me repeat a question for mostly people can see everybody the question, so I don't have to repeat it. The question is, when you look at this fancy new image I had of this one, let me go back here, of imaging a black hole, and you look at some of these exotic images of atom, they look similar. They look similar not because they are similar, atoms and black holes. They look similar because we are looking at both these objects in a threshold of our capabilities. So there's blurring, there is stuff. and that is why it looks like but in details they are different. And also, one should not compare the atomic world, which is a quantum mechanical world, which cannot be visualized by an image like this in standards, with compared to a black hole there. Priya, is that fine? Yeah. Okay. So I would be okay if anybody else wants to ask a question by unmuting themselves or.
Sir, am I audible?
Yes, you are.
Sir, I'm Janish Gupta from Calcutta.
Yes.
Sir, it was a really mesmerizing lecture. It was really fantastic.
Okay. So everybody heard the question. The idea is about primordial black holes. Our status in primordial black holes is the same as we were in 1940s about black holes. There are some people who have said that it's possible, just possible, to produce primordial black holes. So the can question has been partially answered. There are a lot of people who think that is not possible, but some people think it is possible. The can question, can primordial. So that is the status out in there. The status of the question of whether we have observed them, the answer is no. We have found virtually zero evidence for any primordial black hole ever. Also a contention that whether primordial black holes could be something called dark matter, and for most of the space of primordial black holes, this has been discounted. If primordial black holes are of a very particular kind, and they can still explain dark matter, but it's highly unlikely in everything. So that could be an issue. Is that maybe you have to wait for another 50 years to answer that question, if that would be correct. Let me take a question from chat first and then go back. It might not be. Thanks. It might be. But when I gaze stars and planets in the sky, then it shows bright reddish or yellow color. Oh, so you're saying that if you look at different stars, you can see that they are bright, different colors. Like if you see a Mars, it looks reddish. Stars look different. Reddish. So the question is, how do you distinguish they're moving away from us or away? Oh, we don't look at the brightness or the color to know that they're moving away or coming close to us. We look at a spectrum, which your eyes can't do. It takes an instrument, we measure the spectrum, we see something called an emission line in the spectrum, and we see the emission line is shifted, and from the shifting of the emission line, we figure out whether the object is moving or not. Right? Is that okay, Ayush? It's not by just looking at stars that we know whether light is moving away from us. Yes.
Yes, sir. So, I understand that by observing the emission spectrum, we can distinguish.
I'm sorry, are you Ayush? But I can't hear you properly, so you might as well want to type it out. Okay. Let me see if there was. Junik Sengupta wants to. Okay, so let me take.
Sir, may I have a second question, please?
Okay, Junik.
Sir, my second question was that what determines the direction of the formation of accretion disk? I mean, they are rotating, so what determines in which direction they will rotate?
That will depend on the direction which the regular star is orbiting the black hole.
So it is not something to deal with the black hole's spin or its momentum. The direction of the formation of the disk.
No, it'll be first importantly determined by the direction of the motion of the star going on the black hole. Now, during formation of the system of the black hole and the star, there could be forces by which they could have aligned together, but that's a different matter. But the accretion disk will form with the alignment. It has nothing to do with a black hole out the spin to black hole, right? Okay, so let me go to Vaishali. Let me see if I can get.
Thank you, sir.
Vaishali. Yes.
Hello, sir.
Yes, Vaishali.
Am I audible?
Yes, you are Vaishali.
Yes. Thank you so much, sir, for this wonderful session. Actually, my question is also related to the primordial black holes. That I have read on internet that the smallest primordial black holes may have evaporated by now. So my question is it possible that after some millions or billions of years, the black hole which are exist today will also evaporate?
Uh, uh, Possible, but your number is wrong. It is not millions and billions of years. It is millions time billion. It's billions of Hubble time. Did I? So you see, the whole universe is 13 billion years ago, or 14 billion years, right? That's the kind of age of the universe we have. For any of these black holes which I showed you, for them to evaporate, it would or go away, it would take, according to mathematical calculation, which is probably wrong, a million times the age of the universe. So it's practically not possible. Did that answer your question, Vaishali? It takes a very, very long time. But a
Yes,
primordial
sir.
black
Thank you.
holes, which are very small, they could have disappeared, but that is fine. But first of all, let me explain you. This is a complete different footing. We do not know that primordial black holes exist. We are not even. The biggest job is to, before you wonder about this thing, you have to find them first. If you don't find them, nobody's interested. Yeah, right. So now let's get me to Ayush Garg. So I didn't quite understand. The yellowish color star is due to the bright luminosity or because of increasing distance. I'm not sure I understood the question very well, but anyway, it's not very connected to my subject, so I'll skip that and see if anybody else has any questions. Okay, so then I think we can pause now, and I'll talk to you again tomorrow at this time, and I'll talk to you about just to give you. I talked to you about something very important. I talked to you about how we actually do science and what is the means by which uh, we find out and get knowledge about astronomical objects which are very far away. So I will, and something called relative processes, which I'll go into in my next class. Okay. Yeah, two people raise hands. Abhijit.
Yes,
Yes.
sir. We have been hearing about this intermediate mass black holes.
Yes, I'm sorry. Abhijit, I missed your question. I will answer that. That's interesting. See, today Abhijit, that's a good question. I talked about two things. One was these X-ray binaries, which have kind of black holes which have the mass of around 5 or 10 times the mass of the sun, and then the center of a galaxy which has a million times mass of the sun. Then there are sources which are billion times mass of the sun. So between 10 and a million, there's a lot of numbers like 100, 1,000, 500. And for a long time, we did not have any evidence any direct good evidence for the existence. Earlier, we had some evidence that from far away galaxies, we could see some objects which seems to be very bright. We are not sure they are black holes, but they seem to be having intermediate mass black holes of 100 or 1,000 solar mass. But that was a controversial subject. One thing which has happened in gravitational waves astronomy is that now we have seen 100 solar mass black holes, which is the largest kind of black holes of the lower end side, 100 solar mass black holes. See, so let me explain. The maximum mass we had seen before was 15. From the X-ray binaries point of view, the smallest mass we had seen was at 2 million. So between 15 and 2 million, there was a big gap, and there have been hints that there could be a possibility, but we're not sure. Now with gravitational waves, we have gone to 100 solar mass, but we still have that big gap of 1,000 or 15 solar mass we are not seeing. There's some interesting clues from some objects which seem to suggest that there could be objects which are 1,000 solar mass black holes, but we are not sure yet. So that is going to be a very interesting part of our discovery in the next 10, 15 years, to make sure that if we identify them and get proof that they are actually 1,000 solar mass. Right? Okay. All right. If anybody else has any questions, I can't see anything in the chat box or raised hands. So fine. So shall we meet tomorrow? Okay. All right. Okay. We can adjourn for tomorrow. Bye, guys.